In the previous session, we talked about normalizing flow and especially the autoregressive version. Today, we want to complete our discussion about normalizing flow and start another generative model, which is a bit different from the perspective of the metric it uses to fit the model, which is GAN. At the end of the class, we will start that part. But as a reminder, what we had before, let's talk about the last part, which is inverse autoregressive flow. This was, maybe you may remember. Real MVP, and this was mass autoregressive flows. In the mass autoregressive flow, it is exactly similar to autoregressive models we have seen before, where to generate the new sample in your observed data, the new element in the observed vector, you need the previous ones that you observed. As a result of this type of formulation, we see that sampling in this model is sequential. Why? Because first you should generate x1, then you can calculate the statistics needed to generate x2. So sampling is time consuming and it is not efficient in terms of calculations and computation. But on the other hand, likelihood calculation, which is needed for learning, can be done in parallel. How? For likelihood calculation, you are given a vector x, a vector of observed random vector. Then you can easily calculate the mu and alpha vectors. And because we access to all the vectors, all the observed vectors, you can easily calculate each of element in parallel. So you have compute mu and alpha in parallel, and then you can calculate z using this transformation, which is the inverse of what you have done to generate x, and we know how this can be done. And finally, you can calculate the likelihood that you want using the change of variable trick or theorem. How you find z, the likelihood of what you observe is the likelihood of that z, which is normalized using the determinant of the Jacobian matrix as we see before. And the determinant of the Jacobian, as we see in the MAF, mass autoregressive models, is this term. So on the other hand, the likelihood calculations is in parallel, so it can be very fast and it is efficient in terms of learning the model because you can easily calculate the likelihood in parallel. Today I want to talk about another task or another interesting idea, which is conditional modeling using normalizing flow and especially mass autoregressive flow. Why? Yes?
Last time I did not understand how do we get x if x2 is dependent on x.
You want to generate. You are in the phase of generation, okay? So in the generation part, you have access to z. You generate one z. So you have all the elements of z. And it is equal dimension as your x. The first part, the first element of x can be easily generated. How? You multiply it by the exponent of alpha 1. We know that alpha 1 is a function of x less than 1. X less than 1 is nothing because there is no element. So we assume it a scalar. And also, a mu1, which is also a function of x less than 1 is added. Again, this part has nothing to do because there is no element there. And you generate the first element, x1. So the first element is generated. For the second element, we need one multiplication here and one addition here to generate x2. But we know that this multiplication is done exponential is done by a real value alpha 2, which is a function of x less than 2. X less than 2 is only x1. And you previously generated x1, so you can use it here as input to this neural network. And also for mu2, which is a function of x less than 2, or equivalency, which is a function of x1, you again use this x1 here and generate mu2. And until the end. Is it clear? Okay. Now we want to talk about conditional generation. At the start of the term, we see that there is no difference between conditional generation and unconditional generation. And in autoregressive models, we see that how we can apply conditional generation by adding the condition or the label as an input to all the factors in your chain rule. We previously see that. Now we want to know how we can use conditional generation in autoregressive flows, and especially masked autoregressive flow. Now, assume that you want, instead of, for example, MNIST data, you have access to both MNIST images and also their labels. You have the labels, and you want to generate, and you want to model this distribution. As you can see, this is a random vector, and this is the input vector. It is not random. We want to model this distribution instead of what we have previously done, which was this distribution. Okay? So here, pay attention. First, y is not a random variable. So you cannot treat it as you treat x. It is not random. It is a given vector. Second, y is given, so we must design the invertible transformation assuming you have access to y in both forward and reverse transformation. What does it mean? Assume that I want to design the forward transformation. It means that in the forward transformation, you can consider y as an internal value which is given to your function. It is not a random vector, and you do not need to model it. It is just an input vector to your f function. As an example, for example, you can use this formulation. Previously, in the unconditional case, you have no y, so you just need x1 to be dependent on z1 and also the previous x's, which is nothing here for the first element. So by omitting y, you have exactly the previous one. But because you have access to y, you can use y in your transformation. In other words, the y, the label of that image, can affect your transformation, and also the Jacobian and everything we have calculated before. So this is the forward transformation. And in the inverse transformation, again, y is given. It means that the calculation of y can be done easily, and it is not needed to model y. In other words, assume that this is the inverse transformation. For the inverse transformation, x1 and x2 are given, and I should here generate z1 and z2. And I know that based on this transformation, z1 is easily x1 minus this term divided by this term, and z2 is also as you can see here. But pay attention that I do not assume y a parameter to be changed, a random variable. It is just a given vector, similar as a number, a numeric vector. So this is how you do conditional modeling. It means that the label can easily affect the transformation. So the information of the label can flow through your transformation, and in that case, you can have conditional generation. And as you can see here, whenever you want to generate samples, previously you are given a y. So you do not need to do anything with y. Y is given. And also in the terms of likelihood calculations or generation, both of them. In both of them, y is given. So this is the result of, yes?
Would you please, I'm not getting how this exponential of y factor can help us in the conditional distribution.
Yeah, you know, generally the design, the design how y affects the transformation is a really tricky part. You know, assume that in the very simplest case, this is z1, this is z2, this is x1, and this is x2. It is a naive example. In real-world application, it is much more complex. Assume that I encode y as either of these two cases. I have a binary classification and I encode y as one of these two. And then, in the case of training the model, I said that whenever y is equal to
a scalar, right?
What?
Y should be a scalar.
No, it cannot be. Here is a scalar, yeah. It is based on your formula. It is based on your modeling. It can be, for example, the label of MNIST can also be considered as a number, as an integer, or it can be a one-hot vector.
But here, based on
here is a scalar. You know, how can I affect the? In this case, the y totally affect your transformation. Assume that I consider y to be 0 or 1. Here, if y equal to 0, I have one transformation which is no y here. You do not have y here. Y is just in this condition. And if you have y equal to 1, you have another term, completely different with different parameters. And also for x2, you have again, it means that based on the value of y, you are completely training a new transformation. If y is 0, you have transformation A. If y is equal to 1, you have transformation B. And this formulation can be easily inverted. Why? Because you have access to y, this is f. And in the G part, you have access to y. And again, you can see that say that z equals to this term if y equals to 0. In this part, you can inverse this transformation here, and also for y equal to 1.
I know. My question was, why be like plugging y into our model?
Because you want to generate conditional modeling. How? After training the model, you can easily generate with a specific y. In terms of, for example, language models, or for example, language vision models, assume that you input a text and want to generate the images corresponding to that text. In this case, you need to generate conditional modeling as here. This cannot be used for that application, but for just to make the case clear. Any question about how we do conditional generation and sampling? Okay, after the training this model, for example, our MNIST, you can easily generate samples. This is the middle line. You can generate samples conditioned on y. Here in the first line, as you can see, the authors assume that y is equal to 0 and start sampling from the model. The model is not generating anything other than 0 because it is conditioned on 0. and everything it generates is zero. Different types of zero images. Is clear? In more complex applications, for example, it is a text, and you want to generate images corresponding to that text. Whenever you condition it on a specific text, then the model just generates samples conceptually similar to what you have written there. This is the result of generation for label 1, 2, 3, until the end. This is the class conditional samples. But in the more complex case, the Y can also be more complex, for example, text. More complex data like text, not a label. So here, I think you understand how we model conditional generation using a flow model. But pay attention to our previous examples we have before, which was image in painting. Can you propose another method to have a conditional generation based on this idea? Previously, we see that if you have a missing part in your image, then based on a trained model, you can predict that missing part. Okay? Now, you have a data set. Again, you have the MNIST, and you have the corresponding labels. Can you think of another form of modeling for this problem? I can do this. Instead of modeling a conditional distribution, I can assume that the data is not X alone. X concatenated with Y is your input data. The complete data is the image concatenated to its label. Then you can easily train a model for this, because it is unconditional generation, unconditional modeling. You can easily model these types of vectors. What happens? You vectorize the MNIST image. It is 784, and also you add one element, or even you can add the one hot vector corresponding to its label. You have a new vector, and the dimension is just increased in comparison to MNIST itself. So you can easily model it using a normalizing flow. Okay? Now we want to have conditional generation. What happened? I have a model which is trained on MNIST concatenated with its label. So in this case, assume a similar problem like this example of in painting, where this is the hidden part, and this is what you observe. In the case of, conditional generation, you train the model, you have a trained model for the concatenated vector. Now, assume you are in the case that XO is the label, and it is given because the label is given, and you want to generate sample from, and you want to fill XH. You know, if this is the image, assume I concatenate the label here. This is the label corresponding to 0. The model now, how is the complete the vector? Because it is trained on the complete vector, okay? So when you have this part as observed and this part as hidden or missed or corrupted, it can fill the corrupted part because it has a model how they have correlated with each other. So it feels something like this here. Yes?
Would that model only work with that specific way of concatenating the vectors?
The concatenation and the model is much more complex than we see before, because whatever you have here is much higher abstract than what you have here. This is a pixel level information. This is a label level information. The label is much higher abstract than the pixel. You know, it is not very, you cannot trivially use different previous models we introduced to make the model works. Usually you have something here different, some neural networks here to process it, and some neural networks here to process this part, and after some level of processing they can be merged together, you know. That part is not trivial, but the concept is as we talk about. The concept is that you concatenate them together and then train the model that model the joint. The joint is the most informative things, you know, the joint over the two vectors. But in the previous case, here you also model the the distribution over the labels, you know. Another interesting idea. Assume that instead of considering this part as xh, I consider this part as x observed and this part as xh. What happened here? If I give the model a new x, what does the model say about the second part?
Predicts the label.
Exactly, it's a classification. It exactly becomes a simple classification. You give it the image and it predicts the label. It's a classification task using a generative model. Is this clear? So you can work with each of them. As I said, the joint is the most informative part. It can also be used for conditional generation or classification. And it can be used in either of the cases, although in the previous modeling, in the modeling that we see here, you cannot use it for classification. Here, it cannot be used for classification. Why? Because you do not do anything with y. Y is given. So if you given the model at x, it cannot say anything about the y. But if you model it using a concatenation, then you have everything. You have the distribution over y, you have the distribution over x, you have the distribution over the joint, and everything is in your hand. Okay? Clear? Okay, let's continue. Now we want to talk about an idea. This idea is not when it was proposed, it was not an idea for independent modeling in normalizing flow. It was proposed by the author of the paper, Variational Autoencoder, and it was used to enrich the posterior approximate part in a variational autoencoder. But here we just focus on the main idea of the layer they proposed. But you can see the paper, this paper, where the authors use the resulting formulation to make the approximate posterior more flexible in a variational autoencoder. But here we look at them as normalizing flow models. What happened instead of autoregressive? It is exactly the inverse, the other side of masked autoregressive models. In masked autoregressive models, this part was dependent on x. Here it is dependent on z instead of x. Just this change is applied, and again you have the model that can be invertible. So the first element of what you observe is generated using this formulation. It is multiplied by this factor, and it is this part is added to it. So you have this transformation. The second part, in the second part, you use the Z1 as the input to your variance and bias terms, and they can affect that. So you have this formulation. Previously we have x here, now we have z, where these two are arbitrary neural network. They can be anything. And the inverse transformation is also easy because you generate the Z sequentially. When you want to focus on ZD, you have previously generated Z less than D. Let's see it in a more visual way. So what happened? For the first element, these are two parameters of your transformation. It is multiplied by the exponent of this alpha 1. Mu1 is added, you generate x1. So to inverse this part, you have nothing to do because these are the model parameters, so you can inverse the process and generate z1. For the second one, what happened? For the second one, first z1 is input to your neural networks, alpha 2 and mu2, and generate these two scalars, these two real numbers. And then these two are used to transform z2 into x2. Now for transforming this x2 into z2, what happened? Again, you have access to z1 previously here, so you again generate exact values here and use them to cancel the operations you have previously done. And this process is done until you generate both your observe and also for the inverse transformation. At the arbitrary D element, you input Z1 to ZD minus 1 to generate alpha D and mu D, and then use them to, let's say, modulate the ZD into XD, and also the inverse also can be easily done. These values are exactly the same because you have input the same vectors into your neural networks, so you can cancel the operations to generate ZD. Yes?
How is this different in the previous section on past autoregressive flows?
In the previous part, let me go there, I think it's, here. You know, in the previous part, X is used to generate these two numbers. The previous X generated are used to generate the alpha and mu. Here, Z is used to generate these two. So it is not autoregressive in nature anymore, you know? In the context of stochastic process, you see that this is a moving average type. This is the previous one is autoregressive. This is the moving average. Sometimes you have the mixture, which is ARMA, autoregressive moving average. But it is not important. The name is just maybe for the because you have some inverse operation of autoregressive. It's inverse autoregressive flows, but it is not autoregressive in nature. Do you understand how the previous one was done? Okay. So here we have again a new type of transformation, which is invertible. Okay, and this can be done until the last element. So the most important part is to calculate the Jacobian, the determinant of the Jacobian, because it is needed to normalize the data, the distribution. Okay, so what happened again? You have a lower triangular matrix. Why? Because in this formulation, this is not dependent on the future. Okay, so we have a lower triangular matrix. The lower triangular matrix, the determinant of this type of matrix can be easily calculated using the multiplication of the diagonal elements. So we have the logarithm of the absolute value of the product of the diagonal elements. This is not very far from the previous type, the mass autoregressive. In that part, we have x less than d here. Here we have z less than d. Nothing changed very much. So, because the exponent is positive, you can neglect this line, this ABS line. So we have this summation, logarithm and exponent cancel each other. Okay, so we find the Jacobian, and it is easy. You want the gradient of this value with respect to its parameters, which can be simply calculated using different libraries you have for deep learning. Okay, yes.
So training this model is basically summarized in training the alpha model, yeah?
Yeah.
And we have like the alpha for the model.
They can be shared parameter. Yeah. There are some. They can also share parameters too. There sometimes, there are some networks. This network is generated where the network is d-dimensional input, d-dimensional output, and when you input the data, it generates all of the parameters all at once. Yeah, it is not that complex, but the basic theorem is the basic proposal of this model is based on the fact that each of them has its own network. Yeah, so it is similar to real MVP. As it is not volume preserving, as you can see, the determinant is not, the determinant of the Jacobian is not 1 anymore. Any question? Okay. So let's think of calculation, sampling and or likelihood calculation for the IAF, Inverse Autoregressive Flow. For the sampling, in contrast to the previous one, where the sampling was in sequentially, here the sampling is in parallel. How? Because when you have Z, you can easily compute both of these vectors, both the mu and the alpha vectors, and having access to mu and alpha vectors, you can calculate X using this transformation. So similar to likelihood calculation in the previous part, generation here is in parallel and can be done fast. So you have parallel sampling here, and pay attention that when you want to generate mu, you need the access just to Z, not to X. So this is not sequential. It can be done in parallel, the sampling. But the likelihood calculation has some problems. How? Because in likelihood calculations, first you should generate X, you should calculate X, Z1, then based on Z1 you can calculate mu2 and alpha2, and having access to mu2 and alpha2, then you can calculate Z2. Without accessing to mu2 and alpha2, you cannot calculate Z2. It is exactly similar to sampling in the previous part. The likelihood calculation here is sequentially. After you calculate all of this Z, then you can calculate the likelihood using the change of variable theorem. The likelihood of the model assigned to X is the likelihood of Z in the base distribution times this normalizing factor, and we see that this is the determinant of the Jacobian. And it is inverse because it is the determinant of the forward transformation, so it is -1. Clear? So the likelihood calculation cannot be done in parallel. It is sequential. So training them is time consuming. So this likelihood calculation is sequential, but the MAF and IAF here, generation is slow and likelihood calculation is fast. So they are suitable for training. On the other hand, IAF generation is fast. Likelihood calculation is slow. So these are suitable for generation. There is an idea which is called parallel wavenet. Parallel wavenet is the model which has been used for speech synthesis. You give a text to this model read it for you and generate a speech signal, which is which is your sentence. Okay. Parallel wave uses the idea of both of them together to have both fast training and fast generation. And you can read this part if you are interested in these types of modeling. The most important point in that part is that IAF, although it is slow in likelihood calculation, but if the data generated is generated by IAF, then IAF can easily calculate its likelihood fast. In general, IAF, if you give an input X, IAF cannot calculate the likelihood of this data fast. But if X is something which is generated using that IAF, then IAF can calculate the likelihood very fast. Very fast, it means that similar to MAF. And this is the trick that they use in parallel wave to have a model that is fast in both training and generation. If you are interested, you can follow this keyboard, and there are lots of information in the web. Okay, by this slide, we are at the end of normalizing flow presentation. Just a conclusion and a summarization of what we have seen before. What are the pros? One important point is that you have exact likelihood calculation similar to autoregressive model, and in contrast to variational autoencoder. Variational autoencoder just give you a lower bound. They give you exact likelihood. It is important. You have invertible latent transformation. Why it is important? Because, for example, in VAE, you need an approximate posterior model to calculate Z. Not calculate Z, calculate distribution over Z. Here you have exact Z. Why? Because the transformation is invertible. And also the latent representation can be extrapolated. We see in the previous session that if you extrapolate the latent, you have some meaningful images. This is a feature which shows that the model has some higher level of representation in Z. But we know that the level of representation in Z is not similar to VAE, because in VAE we see that we have attribute vectors. But here, designing the attribute vector is not easy as VAE. And the cons is that the latent is the same dimension as your observed data. It is sometimes limiting because generally the observed data is high dimensional. The limitation for invertible transformations makes lots of different neural networks useless for using in flow models. And also the scalability due to the dimensions. You have D to D transformation. D, which is the dimension of your observed data, and generally it is very large. Okay? And these are our conclusion about normalizing flow models. And this is the list of abbreviations in this presentation. Any question about flow models? Everything is clear? Okay, let's talk about GANs, which is one of the most interesting ideas in generative modeling.
I have a question
about? Yeah, sure.
With its problems with scalability, do people still use them for applications, or have they been superseded by things that don't have scalability?
These types of formulation, this type of modeling, these are the basis for another type of flow models, which are continuous flow models. They are comparative to diffusion models, continuous flow models. The basis for understanding continuous flow models is exactly the flow models we talk about here. And those models are both scalable and also, because as you saw, diffusion models are exactly the same as flow models. They have the latent, which is exactly the same dimension as observed. So it is, nowadays, it is not a limitation to some extent, you know. You have diffusion models used in different applications nowadays. They are exactly the same, even less complex, because the diffusion models have several latents. These have just one latent. But in the continuous, you have something different from here, okay? But the problem is, the point is that, for example, in edge devices and some tasks like that, they may be limited. But for the cloud computing, they are not limited. And the continuous flow models are nowadays usable for real-world applications. Yeah. Okay, it's clear? Any question? Let's talk about GANs. Okay. In the GAN part, we talk about this. Our outline is, as you can see here, but the most important part is the intuition behind the GANs. Okay. Till now, we generally talk about the idea that maximizing the likelihood as a function of the model parameter is a great idea to fit the model. Why? Because it is equivalent to minimizing the KL distance between the P of data and the P of theta. So previously we used this as our metric of distance. Now we want to focus on this metric and see is it really a suitable distance metric or not. Likelihood versus sample quality. Average likelihood and visual fidelity of samples are largely independent of each other. It may be amazing that likelihood is not a representative of what is visual understandability. Is a model that give you the highest, that give you a high likelihood, means that it gives you visually acceptable images when you generate image using that model or not? This is the question, and the answer is no. Surprisingly, the answer is no, especially for high-dimensional data. Here we want to have a very simple reasoning for this idea. I hope it can work and you understand why they are not the same direction. Okay, let's create samples. Excuse me. Great samples and poor likelihood. I want to give you an example where the generative model gives you great samples but poor likelihood. What do you think of the model which give you great samples, but its likelihood is very, it's not acceptable? Assume a generative model that memorizes the training data. What happened? When you sample from that model, it gives you great samples because it generated training data. But the likelihood is very bad. Why? Because it memorized just the training data and it cannot be used for validation data. In validation data, it gives you poor likelihood. Why? Because it memorized the training data. It's clear? So a model that memorizes the training data gives you great samples, but on the other hand gives you poor likelihood over the validation or in real-world application. This is the example. I assume that the generative model is such that it is an average of Gaussian distributions around each of your training data. So it means that, assume that this is you have data. The training data are these three. The generative model is this. So if you sample from this generative model, it gives you these points, and these points are valid points, are high quality points. But The true data distribution, for example, was this. And even these points are high value, high fidelity points. But your generative model do not capture these points. So we easily see a model which has great samples but poor likelihood. The other part is a bit tricky. We want to show you that there are some models that give you great likelihood but poor samples. So in the first part, great samples, poor likelihood, we see it can be easily demonstrated. But in the next part, we want to show a model which give you a great likelihood. It means that in terms of autoregressive models, variational autoencoders, flow models, it is great because it gives you great likelihood over validation data. But when you sample it, it gives you garbage samples. Samples which are not understandable, images which are not understandable. How? Assume I have this model. I train a model and convert this to this one. We want to show that this model has a great likelihood, but it gives you poor samples. Why it gives you poor samples? Why this model gives poor samples? Yeah, in 1% of your trials, it gives you data, great data from the data distribution, but in 99% it gives you random data. So just 1 in 100 give you a great sample. So it is not a good model in terms of sampling, great samples. Yeah. But the other part, why it have great likelihood? It needs some prerequisites. So let's think of the model. This is the model. The model is 0.01. It is, let's say, hierarchical model. You flip a coin. The coin is biased if it is with these two likelihoods. And then based on the result of the coin, you select one of the data or your random noise distribution. What is a lower bound to this likelihood? What is the lower bound to the log likelihood of this model? The log likelihood of this model is the log likelihood of this term, and we know that the logarithm is the let's say if you decrease the elements, the input, the output is also decreased. Okay. If I omit this part, which is a positive number, the result is lower than the upper part. So the logarithm of this term is the logarithm of the first one plus the logarithm of the second part. The logarithm of the first part is here, the logarithm of the second part is here. And we know that the logarithm of 100 is, the minus is that it is 0.01. So we find a lower bound to the model likelihood based on the data likelihood. And if I calculate the expected value of this data likelihood over all the data coming from the true data distribution, this is exactly what we calculate in training models, autoregressive models, flow models. Even the VAE is a lower bound to this one. So a lower bound to the log likelihood loss is the expectation of the log of the data likelihood minus a very small number. It is not very well understandable that why this is a small. This is a number maybe comparable to this term. So we find a lower bound to our loss function that we used previously. Now we want to find an upper bound. Upper bound can be easily calculated. We know that the K divergence between the data and model distribution is positive, so this relation is valid. Oh, this is a problem here. Here is P data, here is P theta. This is a problem. We want to find an upper bound. This is not correct, and the correct version is here. Expectation over x coming from P data of the logarithm of p data is greater or equal than, here is not correct there, data coming again from the data. Everything is from the data because there is a KL divergence over the first element, so the expectation is with respect to data. Expectation over x coming from the data of the logarithm of p theta. This is the correct version of what we have here. So we found an upper bound. This is an upper bound. This is what we share in normalizing flow, in autoregressive, and to some extent in VAE. VAE is not this term itself, it's a lower bound of this term. But again, it's based on likelihood calculation. Okay? So this is an upper bound to it. Previously, we found a lower bound also to this term. You know, this is exactly what we care. This is a lower bound. So we have this relation. The model likelihood is greater or equal than the data likelihood minus 4.61, and it is less than the data likelihood. Is it clear how we reach this point? Okay. Here we cannot even understand that why this model has high likelihood. We know that it is sandwiched between these two numbers, okay? And if data likelihood is becoming larger and larger, the model likelihood is almost equal to data likelihood, okay? We want to show that by increasing the dimension, this number will be increased. For example, if you are working with MNIST, the order of this number is about maybe 1,000. If you are working with ImageNet, the order is 1 million. When the dimension is increasing, it is becoming more and more sandwiched between these two numbers, and finally you have a model likelihood like this, which has exactly almost the same likelihood as your data likelihood. So it is great likelihood, but the poor samples. Is it clear how we show that the case? Okay. But why the dimension? By increasing the dimension, the data likelihood will be increased. Why? This is based on two examples, but you can see in different references that this is true for general case of distributions. Given a unit variance uncorrelated normally distributed data with d dimensions, the log likelihood of the data will be this one. So by increasing the dimension, the log likelihood will be increased. It is a linear function of the data dimension. Clear? You can find something about how this can be shown in this reference. Also, a simpler case, assume that I have independent and identically distributed elements which form a vector. Then you can easily show that the distribution of the vector, which is the distribution of the joint, is the product of them because they are independent. And so you have d of them. And if you take the logarithm, again, you have the multiplication with d here. This is very simple and very, it cannot be generalized, but the case is general for the distributions with different formulations. Again, you see that the log of the likelihood is a function of the dimension. So, what happens if the dimension will be increased? Pay attention to here. We see that the p theta of x is 0.01 of p data plus 0.91 of Gaussian and standard normal distribution. Then assume you are training a model over CFAR 10 data set with this dimension. The likelihood is about minus 1,000. This is really a typical number. You can see that in papers working with CFAR, the likelihood is of this order, okay? The garbage model has this likelihood. It means that the garbage model is almost near to your data. But the situation becomes worse when you think of ImageNet dataset with this dimension, where the likelihood is around this number. What happened here? The garbage model likelihood is between these two numbers. So the garbage model is almost the same as your data likelihood. It means that the best value you can achieve is the data likelihood here. And the worst of your garbage model is this number. So you cannot discriminate how the model is great or not in terms of likelihood. Why? Because this garbage model generates one great samples in 100 samples. It is clear why likelihood is not a good idea, maybe not a good idea, but in practice it works. But the intuition behind that likelihood can be replaced with something else is this one, can be this one. There are some other intuitions too. So, we have some models that have great likelihood but poor samples. We have some models that have great samples but poor likelihood. So we should think of something else other than likelihood. This is the concept maybe behind the GANs. It is not designed by the authors, but there are some intuition to GANs using this idea. Okay, so altogether we have this sample which has garbage samples, but it has a great likelihood as the dimension of X increases. So based on our discussion, likelihood may not be a good indicator of samples quality. And thus we need to explore more for a better distance or divergence metric to fit the data. Okay, any question about this part? Let's continue our discussion and to see what happened in GATT. Now we want to talk about the foundation of GANs. In this session, we want to design a new divergence metric such that the data distribution, we want to design a new metric, but this new metric should pass some exams. The first exam is that the data distribution must be the minimizer of your divergence. Because when you have you reach the minimizer of your objective, you are confident that you recover the data distribution. The second part is that the distance can be evaluated using samples of p data and p theta distribution. This is the most important point of change. Pay attention to this point. What does it say? Previously, everything we talked about was based on modeling a distribution. It means that, for example, when we talk about VAEs, in VAEs, the encoder part generates something like this. At the output of the encoder, we have the approximate posterior over Z given X. And also in the encoder, in the decoder part, when it is fed with something like Z, we again have a model posterior over what you observe given Z. Now, we want some models. I did not assume that this sign. What is this sign? If this sign is fed with something like Z, instead of generating the parameters of some distribution, for example, generating the mean and the covariance of approximate posterior, the model posterior, or anything, in the case of VA, in the case of flu models, and also in the case of autoregressive, the case is the similar. We just generate the parameters of the distributions. Here we want something that generates X. What does it mean? Instead of sampling the parameters of the model, it exactly generates samples that are coming from the distribution you care about. You do not generate the parameter of that distribution anymore. You generate samples from that distribution. Is it clear how it differs with the previous talks, with the previous models? In the previous models, when you fed the model with, for example, a Z, in the, for example, VAE, it generates the mean and the variance of model posterior over what you observe given Z. It generates the parameters of the model, not samples from that distributions. Here, instead, we assume that I have a module. That module is capable of, when feeding with samples, for example, from a normal distribution, it generates samples from your distribution. It is a bit different from the previous one. Yes?
So, what's the point of sampling in the first two that you were saying, that we have the probability, and then if we sample, we can generate the X?
Yes.
Okay, so it means that in the third one that you now introduced, it means that there is an extra layer of sampling in front of the probability layer that generates the X.
Yeah, but you know, everything will be changed here. How? Previously, assume that I have this type of modeling, and in this type of modeling, I want to use maximum likelihood estimation. Okay, in this way. You have nothing, you have no information about the true distribution, about the model distribution. You just have samples. But here, because you have the parameter of the model, you can easily calculate the likelihood and anything in that case. But here, you just have samples from the distribution of your model. You do not explicitly know what is the model of your, what is the distribution of your model. So, the main important point is that you cannot use likelihood anymore.
And in the above point, what is the like the minimizer of the divergence of what, like between the?
It means, it is that you want some distributions like P. It can be anything. Remember our first image? Maybe I had it. Yeah, this image. I want to search over this area and find the best one in terms of that divergence. That divergence is not clear now. It is a divergence. We want to design it in terms of, we want to have a new divergence for GANs. And we know that likelihood is not applicable anymore because you do not have distributions. You have just samples from the that part. Okay. So the distance. The distance can be evaluated. We want this distance can be evaluated using samples, because sampling from the data is easy because you select from the data, the training data set. If you have a model like this, sampling from the model is also easy because you just feed your module with Z and then you have samples of your model. So we want to go toward the direction that this D can be evaluated using samples from each of these distributions, and it is not likelihood anymore, the log likelihood anymore. Okay, so we should narrow our selections for D. Okay, the generator, now we want to talk about exactly this module. The generator model is a deep neural network characterized by latent random variable Z, this one, and the generator network G theta. It means that you have a neural network. This neural network is fed with the samples from data from a base distribution or latent distribution like P of Z, and then in the output it generates samples that you know it's coming from a distribution, but you do not have access to this distribution directly. You just have these samples. This is the difference with previous parts. Yes?
In the p-data argument of p, like the minimization of divergence, we are finding the best p that minimizes the divergence.
Yes.
What does it mean to p-data equals to that one? P-data is like constant.
Oh no, it's yeah, my mistake. It means that we can type it p theta. We want, it's completely wrong. This is not correct. Yeah, I should omit it. I will update it. We want to find the just this part. Assume this. I have the minimization over p of this divergence.
And p theta is the what model? The GAN model. Yeah?
P theta is exactly this g theta. Yeah. Now we want to narrow down, as we write down here. We want to narrow down our selection for D and also our selection for P. We see that the new modeling is such that this G theta is fed with samples from a base distribution or latent distribution, and then generates samples from your true data, from your model distribution, not the true data distribution. And now, if you have some metric that can evaluate the distance of this distribution, we do not have access to it. With the true data distribution, if you have a metric that can calculate the distribution between this one and this one in a differentiable way, then what we can do, we can update the parameters of this g theta or theta part to make them as near as possible to each other. But the problem is that you do not have access to this one, just samples. You do not have access to this one, just samples. So we need a metric that can calculate the divergence using samples, just samples. Okay? I think this part is not suitable for this time, and our discussion will not be terminated, will be terminated in between. So let's talk about the next part in the next session. This presentation is also sent to you in the Canvas. You can download it in the Canvas. I just sent it before the class. And sorry for it. Okay, we can finish our discussion now. Any question about the idea of GAN, about the flow models?
Just
Yes.
when you say p data, you mean our estimation for the real p data, right?
No, it means that exactly the data distribution.
So we don't know that.
We don't know. Yeah, we just samples from it.
But in the GAN figure, you just mentioned that by modifying parameters of p data, we would like to make it as close as possible to p theta.
No. In the GAN term, the first change is that I have this module that can create samples from the model distribution. We do not have access to this. We just have X's. Second, we also have access to X's coming from the data distribution. Data is exactly what is data. It is what we do not know and we want to approximate. So I need a distance metric or divergence metric that can compare them using these samples. Based on the samples, comparison based on the samples. And you know that here I do not have any explicit modeling of the distribution. In contrast to, for example, VAE, where I calculate, exactly model the distribution. It means that at the output of this module, I have mu and sigma 2. And then I generate the distribution. This has much more simplicity because if you want the output to be a valid distribution, it must pass several axioms of probability. And you see that in terms of energy models, then we have lots of problems. Again, in energy models, you have similar thing. You do not have the exact model distribution. but you have to obey the axioms of probability, and that makes everything very hard. Yes. Any question? Thank you very much. Have a great day.